Hey folks, sorry that I'm having to do another recorded lesson. I have a meeting during second period today, and so I'm not going to be able to give the notes to second period. So therefore, I might as well give everybody the notes this way. And I can't give notes on Friday, so we kind of have to get this done. Okay, just a reminder that we have a test on next Wednesday over this projectile material. Make sure that you are comfortable with this. It's going to be horizontally launched projectiles as well as the stuff that we cover today. All right, so we're looking at projectiles at an angle. All right, so if we look at this graph here, this graph is also on your little note sheet here. If we look at a projectile path of something launched at an angle, you can see how it travels kind of in that parabolic form. But notice at the launch, notice how this velocity here can be broken up into an x and a y component. And that's part of what we're going to talk about today. All right. And now notice that this first one, it's VO, but really it's VIX and VIY. But notice the x value. What do we know about the x value in projectile motion? The x value never changes, right? So VX, VX, VX. Notice that these lengths of these are all the same. Right, in the x direction. The velocity in the x direction never, ever changes. Now, on the y, notice that it starts off really, really big, right? This one, and then it gets a little bit smaller. Then it goes to 0. Then it becomes bigger, but downwards. And then it comes back to the same size over here. Because remember, when we throw something up, the return velocity is the same as the initial velocity, just in the opposite direction. Right? And notice that this whole thing has a certain symmetry to it. This vector here and this vector here are basically the same, other than one's pointing up, the other one's pointing down. Okay, so what do the x and the y's tell us? We know that the y is going to help us find the height and then the time in the air. Right? Gravity is going to affect how long it's in the air, as well as the height, of course. Right? The x is going to tell me the range, how far, the horizontal distance. Google picture. Horizontal distance that the projectile will cover. Okay, now, if you did the lab yesterday, hopefully you noticed something about the angles that gave the same range. If you notice, you might have noticed like 30 and 60 gave the same range, 25 and 65, 10. Well, you didn't do 10. 35 and 55. If you notice, when you add these numbers together, you always get 90. Right? And remember, two angles that add together that add to be 90 are known as complementary angles. Right? And so if you have a pair of complementary angles that add up to 90, they give the same range. Right? So the same range for a 30-degree angle and a 60-degree angle. And the difference is, if I launch something at a 30-degree angle, I'm going to bring that down. If I launch something at a 30-degree angle, it doesn't have as much height, so it doesn't go up as high, but it moves faster in the x direction. A 60-degree angle launches it higher into the air, so it spends more time in the air, but it moves more slowly as it moves across. All right. Which angle will give you the maximum height? Well, wouldn't that be straight up and down? 90 degrees. Right. And which angle gave you the maximum range? Which one went the farthest? Well, what's right in the middle between 0 and 90? That's 45 degrees. And you should have seen that on your graph. When you drew that graph of, what was it? It was range versus angle. That this one right here should have been about 45 degrees. So the angle gives you maximum range is 45. All right, so well, again, let's revisit what x and y's tell us, right? The y tells us height and time in the air. Larger angles give higher heights and longer hang times, longer time in the air, right? The range is x. Complementary angles give us the same range. Closer you are to 45, the closer you are going to be the longest that you can go. Okay? Due to the symmetry of the trajectory. Let me move this one more time. Let's move my picture. Trying to move my picture here. Hang on. Move it down here. Right. Due to the symmetry of the situation, right, the landing velocity is the negative of the or the landing angle is the negative of the launch angle. Sorry, trying to move this out of the way again, but I'm having trouble. I'll just move this over here so everyone can see it a little bit better. All right, now, see how the angle here is positive. Notice the angle here is the same angle. If this is theta, this is just negative theta. So the landing angle is the negative of the launch angle. And that's because of the symmetry of the trajectory. All right, now we're going to do a little bit of review of the right triangle. Most of you should have had this in one of your algebra classes. Right? If you haven't, you'll learn something new, but it's something that you should be able to do. Okay, so if you remember, we have, if we have a right triangle, we know we have two sides and the hypotenuse, right? And we know, of course, we know how to do the Pythagorean theorem to find hypotenuse. But how do we, but sometimes we know what the hypotenuse is and we want to know what the two sides are. Okay, and so we just remember SOHCAHTOA. We're gonna focus on basically SO and CA, and we won't do the TOA as much. So we're gonna use sine and cosine here most of the time. But sine of any angle is on a right triangle is the opposite side over the hypotenuse, and the cosine of any angle on a right triangle is the adjacent over the hypotenuse. So we're gonna look at those two equations. Okay, so I'm gonna slide it down here so we can see this a little bit better. Okay, so I have this right triangle. Oops, hang on a second. Let's see. All right, I'm not sure what happened. So this is supposed to be a side of 3. Okay, so let's find what y is. Okay, y, and we know this is a 40-degree angle. Sorry, this is a 40-degree angle. So the opposite side is y, and the hypotenuse is 3. So we know. Let's move it over here. Look at it here. So the sine is opposite over hypotenuse. So the sine of 40 is y over 3. And then if I multiply this both sides by 3, we get y is equal to 3 times the sine of 40. Put it in your calculator, then you get 1.93 meters. Make sure in your calculator you are in degree mode. Okay, depending on what type of calculator you have, you might have to do a bunch of different things. Right? You might have to hit mode, or there might be a DRG button. But when you have your calculator up, somewhere at the top of the screen, somewhere towards the top of the screen, there should be something with a D or a DEG on there. If it says, if there's an R or RAD radians, you need to change that. If you're not sure how to change it, go ahead and if you're in my class, come talk to me tomorrow. If or not, Zoom me during one of our Zoom times. You can come on in and I'll show you how to do it. It won't be, it's not too bad. All right. So the other thing is let's find x. All right. So we're doing the same thing. We know cosine is adjacent over hypotenuse because now we're finding the adjacent side. So cosine of 40 is x over 3. And we come up with the final answer of, x is 3 cosine of 40 or 2.3 meters. And so anytime you want to find the horizontal component from this angle, we use cosine. When we use the y component, we use the sine. All right, so same idea over here. Right. This is 20 meters per second. We want to find Vx and we want to find Vy. Right. So if we want to find Vx, we just come over here. We say that Vx is going to be our adjacent side. So cosine is adjacent over hypotenuse. So cosine of 20 is Vx over 20. Multiply both sides by 20. And we get Vx is equal to 20 cosine of 20. And we get our final answer to be 18.8 meters per second. To find Vy, we do the exact same thing, except now Vy is we use sine because Vy is our opposite, so sine of 20 equals Vy over 20. Multiply both sides by 20, Vy equals 20 sine of 20, and we get 6.84 meters per second. Notice because the angle is very low, 20 degrees, the angle is very, very low, most of the velocity is in the x direction, only a little bit of it's in the y direction. As this angle gets bigger, if the angle was 70 degrees, then Vy would have been large and Vx would have been much smaller. Right, so in general, if I have a projectile launching at some angle theta, then Vx, the x component of the velocity is going to be V cosine of theta, and Vy is going to be V times the sine of theta. Okay, you always pick the angle that is to the horizontal, and then these two equations will always work. Right? And the only types of problems that you're going to have to work on a projectile at an angle is to find this Vx and this Vy. So it shouldn't be too hard. All right, so let's look at an example. Okay? A football is kicked at an initial velocity of 16.7 meters per second at a 67-degree angle. All right? They want you to draw a diagram, and first thing, draw a diagram and find Vx and Vy. All right, so this is V, this is Vx, this is Vy, and this is 67 degrees, right? And this is 16.7. V equals 16.7 meters per second. So Vx is just V cosine theta, which is 16.7 times the cosine of 67. And that gives me, plug it into your calculator. Everybody do it with me. Pause it if you need a chance to do it. I get 6.53 meters per second. And then Vy is going to be V cosine. Sorry, not V cosine. Let's try that again. Vy is going to be V sine theta, or 16.7 sine of 67. And we just plug that into our calculator. 16.7 times the sine of 67 gives me 15.4 meters per second. And because the angle is pretty steep, Vy is much bigger than Vx. Right? All right, so sorry about that. Had to pause that for a minute. Hope that wasn't too distracting. All right, so now we're trying to figure out what the velocity is at the top of the path. Okay, well, let's go back and look at the problem again. All right, so it's 16.7 at a 67-degree angle, and we know that the x velocity was 6.53. Right? And so when it reaches the very top, we know that the vertical velocity stops, but becomes 0 when it reaches highest point, but the x velocity never stops. So this value is going to be whatever the x velocity was, which is 6.53 meters per second. And what's the vertical velocity at the top of the path? We said that was 0. And the resultant, the overall velocity, is just going to be 6.53 meters per second. When it hits the ground, the horizontal velocity is still going to be 6.53 because it hasn't stopped moving. It keeps moving in the x direction and never changes. Right? The vertical velocity when it hits the ground is going to be the opposite of when it launched. Well, when it launched, it was going at 15.4 meters per second. So this is going to be negative 15.4 meters per second downwards. And the resultant velocity is going to be 16.7 meters per second. And what angle would hit the ground? Well, if it went up at 67, then it's going to come down. Was it 60? 67 degrees, right? So it's going to come down at 67-degree angle, but in the negative direction. Right? What's the other angle that'll give you the same range? Well, we know that they have to add together to be 90. So this would be 23 degrees because 67 plus 23 is 90. Which of those two angles would it go higher? Well, which one is steeper? That would be the 67 degrees. Then they want me to name two angle measurements that would have a shorter range. Okay, well, we know that as you get closer to 45, it gets bigger and bigger and bigger. So anywhere between 23 and 67 is going to be bigger. So we're looking for things on the outside. So maybe 15 degrees and maybe 75 degrees. What would have a longer range? Anywhere in between here, maybe 45 and maybe 35 degrees. But any in this whole range between 23 and 67. All right. Now, same idea. I want you all to try the second problem. Okay. Do example 2. I want you to draw the diagram and then answer these questions. All right. I'm going to, at this point, pause the video and try it. And then now I'm going to skip ahead and put the answers up here so you can check yourself. Once you try it, unpause the video and check your answers. All right. So Vx would be 5.49, Vy would be 3.84. I'm just going to slowly scroll down with these answers. Pause if you need to stop it to take a look at any of those. I'll stop it right there for a second. All right. So make sure that you can do these problems. If you have any questions, come on and check with me. We're going to have a learning check over this on Monday, so make sure you know how to do it. All right, tomorrow on Friday, you're going to have a chance to practice these some more and come on to ask questions with me. All right, have a great day.